Hi, everybody. Thank you very much for coming. My name is Ben Marsh, and this is my colleague, Ryan Hummer. We're engineers at Epic, working on the Horde and build teams. And today we're going to be talking a bit about Horde and UBA. So if you're expecting any fancy lighting demos or something like that, you're going to be sorely out of luck. So I'm going to start by just taking a sort of big picture, zooming out a bit. Any team that's working on a UE project needs three things. They need runtime, they need the engine, they need the editor, and they need infrastructure. And Unreal Engine's always been really good for the runtime. We've got a really good reputation for that. There's the renderer, all of the fancy tech demos that we do with the physics engine, all that kind of stuff. And it gets us a lot of good press, and people write about it, and it's a big draw to the engine. But I think one of the real secret weapon that we have in our back pocket is the tooling, things like the editor. And compared to when I started out in the games industry, having something like the editor, which is just out of the box, it works, it does a bunch of things, it's got flexibility, it's versatility, it's been battle tested, and creatives can create content without having to trouble an engineer and ask them to, implement some feature or something like that. And that ability to iterate on things, to refine that iteration loop, is one of the most important things that any project can have. That's not the only bit of tooling that we need, though. Pretty much every team has infrastructure provided by either a small DevOps team or an IT department, and it tends to be developed in a very ad hoc way, as and when things are needed, and usually it's done after the fact. It's only done once you realize there's a problem, and it's not sort of very proactive and so on. But that stuff's really important because that's the stuff that glues the team together, that allows people to work together. That's the thing that defines the workflows, not just when you're working on your local machine, but when you're working together, when you're sharing content and how you actually ship something. These are some of the things that we've been involved in on DevOps teams at Epic. And there's a lot of stuff there. There's a really broad remit, and it's kind of messy, and we're responsible for a lot. And each one of these things is key to somebody's workflow. It's really difficult to take one of those things out and not interrupt somebody. And the way that we typically approach trying to solve these problems is to bring in third-party solutions to them. So you might bring in Jenkins for your build automation system. You might bring in Incredibuild or SNDBS for build acceleration. You might have something like Media Shuttle for distributing builds and so on. And they help to a degree, but the more of these things there are, the more complicated all the glue becomes holding these things together. And after a while, all of the glue and the duct tape and the trying to fit square pegs into round holes and all that kind of stuff becomes, it ends up shaping the solution more than if you designed it from scratch. And as an engine provider, we want to do better than that. We want to make it so that the infrastructure that we design can grow along with the engine as well. So 4 or 5 years ago, we started working on Horde. Horde is two things, really. First, it's Epic's attempt to try and bottle up the golden path that works for us and share it with other people so that they can use the same workflows that we do, because the workflows and the infrastructure is battle-tested and dog-fooded in exactly the same way that the rest of the engine is. The other thing that it's attempt to do is an attempt to build a platform for building more infrastructure on in the future. One of the nice things about being in the industry, I think, is that it's a creative industry and you're always solving new problems. But sometimes you're kind of reinventing the wheel and sort of solving some boilerplate stuff that you don't really care about. We can't really anticipate all the things that we're going to need in the future, but we can look to the past and see certain classes of problems, certain patterns that we've seen before, and we can design things to try and make those sort of problems easier to solve in the future. So almost like building an engine for infrastructure in the same way as you'd build an engine for the runtime or the editor. You might have heard about Horde before, probably in the context of a build system, which is definitely a big part of what it is, but it was never the whole story. It was never where we intended to leave it. Build systems are one of the first pieces of infrastructure that any team tends to set up, and they end up being sort of focal point where everybody rallies around. There's a lot of maintenance that goes on with them. There's a lot of workflow things that feed into them. So it's a really natural place to start a bigger conversation. That's certainly where we started from. And in the past, we had a third-party build system that we had a lot of scaffolding and duct tape around to try and make it work in the way that we wanted it to. And we started to think about what a better solution would look like for that stuff. This is kind of where we got to. This is what Horde looks like today, or at least the ecosystem around Horde. And there's a lot of stuff in it. This isn't like a fixed diagram. It's constantly sort of changing over time. We're adding more sort of extension points and so on. But it's important to notice that even though the build automation system is right at the center there, there are lots of other things in there which are to the side of it, above it, below it, and various sort of degrees of connections to it. And really, it's the interplay of all of these things together, which is the value add, the thing that we're trying to optimize for. So for the rest of this talk, I'm going to use this diagram as a jumping off point. I'm going to go from the bottom to the top, talking about how the various layers of Horde fit together to create all of the user-facing stuff that we want to share with you guys. So I'm going to start off at the bottom with the server itself. We've shipped server components before as part of the engine. I was responsible for a bunch of them, and I probably didn't do a very good job of productizing them. In general, it's quite a difficult problem to solve just because infrastructure by its nature kind of has like a bunch of external dependencies on things. And when you give it to somebody else, it's very difficult to sort of explain how they would deploy those sort of other external dependencies alongside in a way that really fits the way that they want to work without being too prescriptive about, it can only work in this particular way. So one of the first things that we wanted to do with Horde was to make it so all of that stuff was a lot easier. So we've got a modern tech stack. Everything's built with C#, with ASP.NET, and it has an integrated web server. We include all of the databases that you need in the box, which in our case is MongoDB and Redis, although you can host your own elsewhere if you want to. But the key thing is that you can just open the solution for it, load it up in Visual Studio, and hit F5, and you've got something up and running. So when you want to extend it, when you want to add new things to it, all of that stuff is easy. When you want to come to deploying it in production somewhere, we have a consistent way of configuring permissions, setting up telemetry, monitoring, and all that kind of stuff. That's the kind of boilerplate that a lot of people, when they start working on tools, server tools especially, tend to ignore. It's very easy to get to the 70% and then sort of realize, all the rest of this stuff that everybody needs when they actually want to deploy to production is not that glamorous and not much fun. And, so by standardizing all that stuff and putting it in a core part of the server, it means that other things can be added on top of it in the future without having to reinvent all that stuff. We very deliberately made it with a modular architecture. So the server has a plugin architecture, so you can add new things into it. There's about 6 or 7 plugins included by default. But you can add your own, and you can enable these things independently and add new functionality if you want to. There's also one of the other bits, which is very easy to underestimate how time-consuming it is making good client libraries for that stuff as well. So when you want your client, like your, say, like desktop workstations or something like that, want to be able to connect to this thing, then you need to configure what the connection should look like and manage that connection and the credentials and stuff like that. So all of the client libraries that we have also handle all of that stuff for you as well. We've got some quite nice C# libraries that go along with it that allow you to sort of interact with things, objects on the server in an object-oriented way. But there's also a full REST API for everything as well. For Epic, especially, we were starting to outgrow the small little server room that we had in North Carolina. So there was a definite want to push things into the cloud more if we could do. And so Horde is designed in a way that allows us to deploy things to the cloud. We provide Docker images for it. It's horizontally scalable. But we also include an installer for Windows. So a lot of studios don't want to go into the cloud yet. So if they don't, then that's absolutely fine. And finally, one of the things that we've always been very keen on is making it so the this idea of configuration as code. We want everything to do with the server to be configured through files that can be checked into source control, so that if, well, first of all, we always have an audit trail for it, but also if the worst happens and we have to redeploy everything from scratch, it's all there and versioned, and we can find it all. So that's the basic layer of things that of the server that we're building on. On top of that, there are two really important foundational features that the rest of the stack uses: storage and compute. For storage, I think there was a sense that Unreal Engine projects are getting larger and larger every year, and we've always kind of been relying on Moore's law to deliver us beefier machines that we can sync things down onto, and there's just a huge footprint of the engine, especially large projects. And so we want to be able to abstract some of that away and move it off people's local machines, make a sort of thinner client that they can work with. For the compute side, we want to be able to enable distributed processing for things as much as we possibly can do, for things like data builds or code builds and stuff like that. We want to be able to take advantage of shared resources that we have, like idle resources that we might have on people's workstations. And not again, the same thing about not leaning too much into, you have to have like a 128 core machine or something like that to be able to use Unreal Engine. And those two foundational pieces are really important in a scrappy creative industry, because we don't want to lose the ability for people to iterate and make new tools and stuff like that. We just want to help scale them up. So those are the two sort of key pieces that we think will help people do that. I'm going to go into a bit more detail about those two things. So first of all, for the storage section, why do we want a new storage section if we already have file systems and object stores and stuff like that? The main thing is that we want to reason about data structures and not files. We want to be able to reason about data structures which are much bigger than something that you might have locally, something that you can sort of iterate, that you can reason about remotely. And we want to build libraries that allow you to manipulate those things in as convenient a way as possible. We also want those data structures to be immutable, because that gives us lots of nice benefits, like being able to cache things and reuse things and so on. At the same time, we want to be able to abstract away what the underlying storage medium is, so we can let the API take care of packing, compression, and whatever the physical storage medium is. So what you're left with as an engineer is just like, I want to grab this piece of data and then follow this handle to get the next piece of data, follow this handle to get the next piece of data, and so on. And they're all small pieces of data that you can load into memory and reason about individually at a time. We want to be able to allow you to reuse those things. So it kind of functions with a garbage collector. All of the handles referencing between different blobs of data that we have. There's a root for each one of these data structures, which is named and acts as a garbage collection root. And finally, we wanted to make sure that there's a danger when you start talking about putting all of this stuff in a custom server, which is that you end up building something that is very complicated and becomes a single point of failure. And we were very keen early on to make sure that we always had, because we're sort of running this stuff in the cloud, we always had the ability to use things like pre-signed URLs for uploading data and so on. So we didn't have to pass all the data through a single server. There are different use cases that you can have for these data structures. So things like content addressable stores is one of them, one of the common ones that comes up. And we build another addressing layer on top of that sort of fundamental storage layer. And that affords us a lot of very nice properties. So it means that we can avoid things like having to worry about transactions when you're adding a new piece of data at the same time as garbage collecting an old piece of data with the same hash, for example. So there's a separate addressing mechanism on top of this stuff if you want to be able to just pull out individual blobs from the store. Onto the compute section. The compute service in Horde is mainly an implementation of Google's Remote Worker API. That's the system that I believe Google uses for all of their internal distributed build systems. So all of the stuff that's built on Bazel and so on, it's executed through the Remote Worker API. The way that it works is that clients describe a piece of work using a fairly small protobuf message, and then pass it to the server with a set of requirements for the machine they want to execute it. So you might say, like, I want you to run this program, and the message will say the program sort of points into the storage system over to the side. So the message is still quite small, but I want you to run it on a machine that has 32 cores, and I want you to give it 64 gigs of RAM. Give that to the server, and the server can find a machine that's going to execute it for you. There's a few ways that you can, I should say that there's a few, first of all, that idea of a message describing the tasks you want to execute. There are a few types of that built in that the Horde server understands, or the Horde agents understand natively. So there are things like, I want you to restart yourself, or I want you to take this program and just run it in a little sandbox, or I want you to sync down this change list and run build graph or something like that. But it's a very generic system, and you can add more tasks as you need to. The server doesn't really care. It just needs to know this is the message, these are the requirements of the machine you need to execute it on. We've kind of designed it to be able to support different types of workloads as well. So there are types of workload where you might sort of say, I've got this message describing a task that I want you to execute, and I want you to queue it up and execute it as soon as you can do. So that's the kind of thing that like a build automation system would do. But you can also say, hey server, give me a machine as soon as possible. Give me a machine straight away. Just sort of poll it. If the server has a machine available, it'll give it to you, and then you can communicate with it lockstep. So you can then open a socket to that remote machine, and you can talk to it, and you can just issue commands directly to it. And that keeps all of the data flow off the server and allows us to scale up without having a super expensive server to run as well. The server does support tunneling at a very low level, sort of low-level packet tunneling, which allows us to, in our case, allows us to run all of our build infrastructure in the cloud, but allows people working from home to connect through that tunnel to remote machines that are hosted inside AWS. All right, so that's the foundational stuff done. Now we get to talk about the more interesting user-facing features. So to start off with, there is analytics. So the analytics system in Horde is a fairly straightforward thing to send data into. You basically just send JSON objects to an unsecured endpoint, and Horde can route that into its own database or route it into some other database you have set up. You can define ways that you want Horde to group those events together using JSON paths. So you can say, like, I want this property and this object to be a sort of unique key, and everything with the same value for that property will be grouped together. And then you can tell it to create metrics from certain things. So you can say, I want you to average out this field, and it will do that over certain time intervals. So there's a few other things you can do, like min-maxing certain fields or creating percentiles and things like that. And once you have those metrics, you can query them directly if you want to through the REST API or through the C# client libraries that we have, or you can get them to get the Horde dashboard to graph it out for you. So you can define charts that say, I want you to show this metric over a certain period of time and group it by stream or whichever project's running and so on. And that's like a super flexible system that lots of things can integrate with. At the moment, we've got a plugin for the editor called the Studio Telemetry plugin. The Studio Telemetry plugin in the editor, but Unreal Build Tool sends telemetry as well. UBA, which we'll talk about in a minute, does as well. So does UAT. And even Horde itself can send analytics data to itself. So you can track build times and things like that over time. Next, the build automation system, which is the kind of the centerpiece of all of this stuff. we've long been developing lots of glue, as I mentioned before, for what our build process should look like, and been relying on third-party solutions to execute it. When we started with Horde, we made it so that it could understand that sort of model of a build process in the same way as we describe it natively. So Horde understands build graph, which allows you to very easily sort of express dependencies between different steps that need to run and the artifacts that need to be transferred between different steps in order to be able to make that work. So it kind of really helps you to parallelize your build processes without having to do a lot of legwork in actually moving things manually to machines and so on. At the moment, it's fairly Perforce-centric, which I mean, befits our use case. We have started to add support for other source control systems and sort of stop relying so much on change list numbers for everything. But I think for the foreseeable future, we're going to sort of primarily be developing and dogfooding it using Perforce. That affords us some nice properties as well. So we have a bunch of tools that you can download and install in P4V that will automatically take a shelf that you have in Perforce and run what we call a pre-flight on it, which is like a job that will unshelve it on top of another change list and then execute it on the build farm. And there's also pre-flight and submit workflows. So you do exactly the same thing, but if the build succeeds, then we check it in for you. So I think Fortnite right now has a sort of mandated pre-flight and submit workflow. So everything that people want to check in, they have to run through the build system first. And like everything else in Horde, the configuration is stored in source control. So that gives us the very nice property that you know, if you're working in a particular stream, all the configuration for that stream is checked into that stream as well. So all of the job definitions that you can run and so on, they're all stored alongside the build graph script and everything else. Epic, more than anywhere else that I've worked, really, really loves log files. And our previous build system really, really used to frustrate people with how bad it was with dealing with 500 meg cook log files and so on. So one of the things that we wanted to get right in Horde from the start was that, well, it can scale up to displaying those sort of things, but it's all fully virtualized as well. So you can just like scrub the scroll bar up and down and it'll automatically stream in the right place, the right parts of the file. That's all using Horde's storage system as well. And we also index the logs as we ingest them as well. So we take all of these, we decompose all of the text into n-grams and build up Bloom filters for different chunks of the log file so that when you start typing in a search term in the top, no matter how big the log file is, it'll very quickly show all the results in the file. I think one of the killer features with this stuff, though, is the support for structured logging. If you haven't encountered it before, structured logging is basically you kind of write, when you're writing log entries, rather than just outputting text, you output like a little, in our case, a little JSON object for each line. And that preserves a bunch of metadata for all the various things. You can think about it like a print format string or something like that. So it saves off both the formatting string and the individual bits of properties and bits of data that you want to insert into that format string. Why would you want to do that? Well, first of all, it makes it machine readable, but you can also annotate it with extra bits of metadata that allow you to do some really cool things with it. So if you have a look at the example here, we've got a compile error, and it's showing you a list of files that contain the compile error. And then at the bottom there, it shows you one of the lines which has been expanded into multiple lines so you can read it more easily. And things like the file names that are in those error messages, those include like a path in Perforce as well. So you can like click on any one of those and it'll open up the P4V time-lapse view and see who changed it or whatever the state of it is at any particular moment. And there's a few other little party tricks that we have like that. So you can click on, I mean, this is I think this is a Mac compile error. But if it was a Windows compile error, you could click on the error code and it would take you to MSDN. If you have an artifact that's being produced as a build, you write a log, an ID to the log of that artifact, then you can click on it and it'll open up a little file browser so you can see all the files that are in there, that kind of thing. And having this stuff being understood natively by the Horde dashboard is really valuable for those kind of like little value-added workflow things. It's been quite a lot of work so far to try and move things towards structured logging, and we've put quite a lot of time into doing it. We support structured logging from all of our C# tools, so automation tool, Gauntlet, build graph, all those sort of things. But we also have support for it in the editor as well. You can write or inside the engine. You can write structured log messages, and they will look like plain text by default, but as soon as you turn on JSON logging, then they will come as like fully decomposable objects that have all this extra metadata in them. So we're going to keep on adding more and more of that stuff because it's super, super valuable for a lot of the things we've been trying to do. One of those things which is super valuable is the build health system. Once we have this kind of more structured representation of what an error is, then we can do things like trying to match it up from build to build. And we can figure out like, oh, this build started failing with this error at this point, and it continued until this point. And we can, because we have all of the paths of the files that caused a compile error, say, we can look up in Perforce who checked those things in, and we can figure out, oh, okay, so it was probably this person that broke the build and so on. We have like quite an elaborate workflow around this stuff where whenever a build health issue like this, you see it also tracks things across different streams and can deduplicate things. So when we have it merging down between different streams, then we can try and figure out like, oh, this is actually this error in Fortnite mainstream was actually caused by some change that was checked into a Fortnite release stream, but it was automatically merged down. And we can correlate them all to the same thing. Yeah, so we have a like quite elaborate system tacked onto this, which is all included in Horde as well, but it's based around Slack and being able to quickly triage these things. We always found that with putting things like this in Jira, it really wasn't suitable for the time-sensitive nature of, you've just checked in a file that has broken the build, so you want to know about it as soon as possible. So what we do is we spin up a Slack thread, we bring in all of the people that we think are responsible, and then right there from Slack, you can say like, oh yeah, this was me, or oh no, I fixed it in this change list. And it will update all of the stuff that you see on the Horde dashboard for you. We do have an option to take one of these build health issues and export it into Jira, but we try and sort of discourage people from using it because usually if you're leaving the build broken, then it's better to back out your change rather than just say, I'm going to fix it in a month or something. So there's also an artifact system for being able to track all of the builds that you produce as part of the build automation system in Horde. That allows you to attach metadata to build artifacts that you produce so that you can quickly search things and get a sort of temporal sense of what's happening to them. So you can find the same build that was done from a previous change list and so on. And you can browse all of those things inside the dashboard itself, as you can see here. You can also download it through UGS, or you can use a tool called Unsync that is checked into the repo, which will take a folder that you have locally and patch it to use this new version of the artifact. All of the artifacts that we upload to Horde are all chunked along content-defined boundaries and deduplicated. So you can very quickly patch your current build into a new build without having to download everything. One of the other cool things that we have as part of this is that if you're uploading a build that has symbols in it, like PDB files and so on, because of the way, because of the stuff I mentioned before about being able to address things in Horde storage using different mechanisms, you can address just the PDB files using addresses that look like symbol server addresses. So you can use any artifact that exists in Horde, you can download the symbols for just by setting your symbol server to be the Horde server. That can be a bit problematic because symbol servers don't usually support authentication. So we have a local proxy server that you can run that you can connect to a local host address, and it will do the authentication for you, pull down the symbols from Horde, and just return it to the debugger. After that, we've got a device management system. So the idea with this is that you can add all of your console and mobile devices to it. And both the automation system, so things like tools like Gauntlet, which is useful for orchestrating sort of multiple client builds against a single server and on different platforms and so on. It can grab devices from Horde and deploy builds to them and run them and get results and so on. And individual users can use this as well. So if you only have a small pool of dev kits, then people can come and check them out and reserve them for a couple of days or something like that and have them automatically checked in once they're done. It's also useful for being able to flag that devices are unhealthy and so on. So if there is somebody that needs to maintain or fix them, then they've got a very clear place that they can go to find it. That device management stuff feeds neatly into the automation hub, which is another feature in Horde, which we use for tracking test results. So Gauntlet can upload results of all of the test suites that it runs, and over time, with all the metadata about which stream and platform variants and stuff like that it's running, and present you with this nice graph where it's showing you like a sort of high-level summary view of all the things that are passing and failing at any particular time. And you can open those things up and get more detail into individual tests that are succeeding or failing. And you can also chart them over time, so you can see that certain tests started failing at this point, and use that as a jumping off point to, it's happened between these two change lists. So this is my sort of range of suspects that I can pin this failure on. And for things like rendering tests, we also display screenshots inline. So it's very very easy to figure out what the thing it's complaining about is, just at a glance. So that's most of the server-side functionality. There's a bunch of client-side functionality that fits into that as well. So there's the editor telemetry plugin that I mentioned. There's the unsync tool, which is used for patching builds. There's build graph, which is part of automation tool. UGS can talk to Horde natively and manage your Horde connection. It can download precompiled binaries from it. There's a new tool in 5.5 called Unreal Toolbox, which we're planning to ship, which is kind of meant to be, in the future, we hope it's going to be a place to sort of collect all of those different tray icon apps that we're creating at the moment. Gauntlet, which is used for automation testing, and Unreal Build Accelerator, for which I will hand over to Ryan.
Thank you, Ben. All right, so yeah, next we'll introduce Unreal Build Accelerator that I'm sure a lot of people are pretty interested in. I know we're very happy with it. So a little bit about Unreal Build Accelerator. It's our in-house solution for distributed compilation work, code compiling via UPT, and as well shader compiling. It's a multi-platform tool, natively supporting Mac, Linux, and Windows. Internally at Epic, we've completely deployed it to our build farm for all projects running UE5, and that's been on the farm essentially for a year now, deployed at scale. And throughout this year, we've been working on solutions to roll out locally to our users. Those are both users in office and working from home. And with this, Horde is the coordinator for Unreal Build Accelerator. It's built on top, using Horde's remote execution system to provide helper resources to assist with compiling. No need to buy into the entire Horde ecosystem. If you just want to kick the tires with Horde, grab that Windows installer, connect some agents to it, configure UBT to talk to Horde, and you're off and running compiling. So a little bit about like the secret sauce, like behind the scenes of how UBA works across all platforms. It's essentially the same concept across all platforms, just with OS-centric implementation details. For Windows, we're utilizing Microsoft detours to intercept all kinds of OS-level methods and other library methods. We're using dlib library injection on macOS. Linux, we're using the LD preload method, and all that we're doing is to intercept OS level calls and transfer data across the wire to the helper agents and transfer it back. So to the helper machines, we don't need to continue to have Visual Studio installed or other tool chains installed. Exception being macOS, just because we can't distribute those. But then to accelerate UBA a little bit more, we compress everything across the wire using OODLE, and we can even compress the OBJ files locally to help reduce that disk footprint. And with all that peer-to-peer communication, we also can support encryption with UBA. So a little bit, but like with the program workflow, how it works with Horde remote execution and everything. You as the local user, or even your build helper agent on Horde or whatever, through UBT, you're requesting a compile. Hey, I want to compile the Unreal editor using the UBA executor. enabling remote execution. It'll authenticate the Horde, upload itself. So the nice thing with UBA, it's not like other solutions where it has to be installed on the host agents. Whatever's there distributed with your version of the engine, so if you make modifications to it, you can upload that to the farm and it uses that. There's no, oh, version 5.5 is on this agent, so I can't use it. It's all kind of locally what you're using, gets uploaded and is compiled. So with uploading that helper agent, and kind of requesting the job through Horde, the Horde server will understand, hey, I need to do 1,000 remote actions. Let me go get you some resources. Once it assigns a resource to help you, that helper agent will immediately download the UBA payload, connect back to you, and immediately start that peer-to-peer communication, sending data up, performing the action it needs to do, and send it right back so you can kind of get all that great compilation time. So in practice, when we deployed deployed UBA to the farm, we immediately doing a vanilla compile of Unreal for our PCP job that we do all the time. Immediate kind of 2 to 3x speed up. Our compile times are in the 15-minute range, a little higher depending on workloads. Immediately we dropped in kind of in the 4 to 5 minute range. Some of the advantages there has been, we're talking about, we are definitely a cloud-centric studio using AWS. So we've kind of, to help some optimizations there for the farm and really end users in this case, some AWS efficiencies. UBA kind of understands AWS availability zones. And when it detects that, it'll promote one of the helpers as a cache agent. So that one will be receiving all the uploads of your CL.exe, your link.exe, all the libraries, whatever. And then all the other helper agents will just collect that from that one cache node. So you don't have to spend your upload bandwidth sending that data around. Along with that, on Windows, we can also do remote linking through UBA. So it's very helpful for compiling the large editor targets when you're linking 1,000 DLLs on a recompile. Some other nice features we have with UBA, as with other distributed tools, we got a visualizer tool, because it's also really important at times you want to diagnose, why is my compile taking so long? Why is it taking long to get helper? So you can get some nice performance graphs of showing, hey, you're IO bound here, maybe your network is slow, or here's this one module that took 2 minutes to compile for some reason. So maybe you need to go and optimize that module. You'll kind of be able to triage that. The nice thing with 5.5, we'll be integrating Visualizer into Unreal VS. And with as of 5.5, the Visualizer is Windows only, but we hope to change that in future releases. And then how we use UBA at Epic Scale. As mentioned, we use AWS. So we're completely utilizing AWS Spot instances for the farm. We run all of those helper agents on Linux, also running Wine. So for our Linux and Windows compiles, we use one single pool to compile either platform natively on the farm. So we have to here's Windows agents for Windows compile, here's Linux agents for Linux compile. Then we also take that a step further as we have a set pool for farm agents and a set pool for user agents, just because there's different use cases between users and the farm. The farm being a little bit more predictable, while end users can be very erratic, and we definitely see spikes of, obviously users don't work in the middle of the night most of the time, so there's a pretty idle point. So it lets us fine tune how we scale up and down the helper resources. And with helper resources for end users, we geolocate those and AWS regions we operate in to give them optimal performance. And with various timings we've done to optimize our costs and just performance, we've kind of gotten our boot times from requesting the agent to start to being helping down to about 20 seconds, just utilizing different flavors of Linux and just getting Wine and everything configured correctly. We do have Mac helpers on the farm to optimize our Mac times. If you saw Josh Adams' talk earlier, he showed how fast our Mac compiles have gotten, going from 6,000 seconds down to 600, or 3,000 seconds down to 600 seconds just by using UBA. So we self-host all of those for the farm and for the users to get their helping. And as I mentioned, remote linking in Windows, we enable it on the farm and encourage users to do it at home as well. It's not very useful for monolithic Windows targets, just sending all the OBJ files for a monolithic game client or any other single monolithic target. It can be not worthwhile. And Mac and Linux are different, where linking isn't really a too costly operation there. So it's really an advantage for Windows editor compilation. So we'll transition now from talking UBA at scale to kind of the rest of Horde operating at Epic scale. So we'll kind of go over some numbers, maybe debunk some information for some folks to say, we are happy with how Horde operates here at Epic. How we deploy Horde at Epic, as Ben alluded to earlier, Horde can scale horizontally. So with that, we're using AWS's ECS setup to deploy Horde. We spread Horde across 12 worker instances, 2 server instances, 2 dashboard instances, that document DB, which is MongoDB, Redis, and of course S3 for all the storage. The advantage here we have with how we deploy it across these worker instances, and we're using Docker and ECS, we can easily upgrade a new version of Horde and do a rolling upgrade and not have to take down the entire farm while we do upgrades, which is hugely advantaged for us as we can essentially continue to deploy if we want to. For how we configure agents on the farm, we use Terraform to do all of our ASG configuration and creation for the agents for Windows and Linux. And for all resources, Windows, Linux, Mac, cloud, or on-prem, we're using Ansible to do all that OS level configuration. Get the Horde agent installed, get .NET installed, Windows, get that Windows toolchain installed, and all the things we needed to get the agent stood up quickly. And lastly, to touch on how we deploy, we do weekly deployments to production for Horde. We kind of make sure we want to do it quickly, try to get out every week just to keep everything fresh and operating, but also in the background, we maintain a development instance where as the Horde team is continually making changes, Horde will see changes to the code, build it, and deploy it to our dev environment. So we're even using Horde to dog food ourselves. To go over some stats for projects running on Horde today, we have 9 individual projects running on Horde. That's Fortnite, MetaHuman, Twinmotion, just to name a few. Taking all those 9 projects, we also then have 60 plus active streams on Horde that we're maintaining and managing. We're always continually adding and removing streams from Horde. Fortnite has its release process where we're creating a stream every 2 weeks, and every 2 weeks we're taking a stream away. And some other projects kind of have that kind of release cycle cadence where we're continuing adding or removing things from Horde. And Horde at Epic is battle tested. It's been powering Fortnite since 2021. It's been used to release UE 4.27, every single UE 5 release, even the preview 5.5 preview 1 that was released just today, and even the early access. And since Horde kind of was developed, and it's kind of the first jobs in the database, we've executed approximately 2.4 million jobs on Horde today. Breaking that down, looking at the last 12 months, we've done about 700,000 jobs. Horde has a concept of leases when an agent has assigned a action of work, and that's approximately 150 million leases executed on the system. And using the storage system, we've seen currently around 2+ petabytes of data come through the system. And lastly, to touch on just the scale of resources we have, we've got a 70-30 split of cloud versus on-prem. Breaking that down, that's approximately 1,100 AWS resources. We don't include UBA helpers there because we dynamically spin those up and down continually based on need and demand. So that's a variable number. We have about 330 on-prem resources. On-prem is self-hosted Macs, Windows VMs that need to talk to interface with devices, consoles and mobile devices, or other special hardware for perf testing. Like we have a suite of editor test resources that are closer to workstation machines, and some performance testing for low spec and min spec machines, and kind of some more of those type of things on the way. And of course, in the 70% area, AWS is all of our Windows and Linux VMs for powering Fortnite and all those other projects. So we'll kind of just give everyone a status update on Horde. Horde, obviously is beta in 5.4, if everyone's seen those release notes. For 5.5, we're going to call Horde production ready. Though as a reminder, it's been used in production at Epic, shipping Fortnite since 2021. We have the Docker images on GitHub. Installers for Windows are in Perforce and also on GitHub. So we're pretty confident with how Horde has performed for us over the years. For UBA, it was first beta in 5.4. For 5.5, we're going to call Windows Host OS features all production ready. So what that means, compiling any native Windows toolchain or any toolchain that you run through Windows, like your console SDKs and whatnot, are all production ready. Shader compilation on Windows is production ready. We've been using that on Fortnite since about March of this year. Shader compilation is when fully switched over for Fortnite to use UBA. And as well, the visualizer is production ready for 5.5. C++ compilation for Linux, Mac, and Windows, Linux and Mac OS is also production ready in 5.5. And as I stated earlier, UBA visualizer is integrated with VS, Unreal VS for 5.5. So we've still other things in the work like shader compilation for Linux and Mac aren't quite ready yet, and some other features aren't quite ready yet for that beta or production level flag yet. And as a reminder, Horde documentation, QR code will take you straight to the Unreal Docs page to find out more about Horde, more information about getting UBA up and running, how to set those up, links to those Windows installers, documentation, source on GitHub, and a spot for everyone to get everything more about Horde. So with that, big thanks to the Horde team, the build team, infrastructure team, been working on Horde for many years. Happy to finally talk with everyone about this. So yeah, that's our presentation. We're happy to take questions. Please come up to Mike if you've got questions.
Oh.